Materials supplied by Microsoft Corporation may be used for internal review, analysis, or research only. Any editing, reproduction, publication, rebroadcast, public showing, internet, or public display is forbidden and may violate copyright law.
Okay, good morning everybody. It's a great pleasure to welcome Gil Herr back to Microsoft. Gil did his PhD over in the computer lab with Marcelo, and he interned here, I guess, at the end of 2008, where he was introduced to the dark side of the Cox theorem prover and compiler correctness. After he finished his PhD, he went and worked at PPS in Paris for a bit, and he's currently a postdoc with Derek Dreyer at MPI in Saarbrücken. And he's here to talk about a subject dear to my heart, which is compositional interlanguage relational verification.
Okay, thank you. Yeah. So, okay. So, software verification is to verify that your software behaves in the way you intended. So, for this, usually you first have to specify the expected behavior of your software, and then verify that the behavior of the software satisfies the specification. Okay. Oops. Okay, and the relational verification is a form of software verification, which is to prove that two programs are equivalent, meaning that they produce the same observable behavior. So, in this case, you can think of it as one program as a specification of another program. So, for example, here, you may want to say that you can show that the correctness of a very efficient implementation of vector library, here vector fast Java, just by showing that it is equivalent to some simple reference implementation, vector.java. Okay, that's relational verification. And what's interlanguage relational verification? That's, it is to verify two programs possibly written in different languages are the same. So here, you may even further optimize it and then implement it in C, which is vector very fast.c. And then you want to show that. You may want to show that this is equivalent to vector fast Java, right? And then what's the compositional interlanguage verification? And this is interlanguage verification, which allows you to compose your equivalence proofs. So for instance, here, you may want to compose these two equivalences to get the equivalence between vector.java and vector very fast.c.
Isn't that immediate?
It depends on yeah, it depends on the notion of equivalence. That's what I'm going to talk about. So, okay. Yeah, this might not be a closed program, right? So it may depend on some open external unknown module. Oh. So it's not clear. Okay, and then so this we call vertical compositionality, but there is another important form of compositionality which we call horizontal compositionality, which is that, for instance, you can further verify that some matrix Java is equivalent to matrix very fast.c. Okay. And then you link these files together to get a library in Java and C. So this is a linear algebra library in Java. This one, linear algebra very fast in C. Okay. And then what you want to do is you verify this one separately, and then compose this equivalence together to get the equivalence between these two libraries, right?
That's not immediate?
Also not immediate. So I will explain.
Observationally equivalent.
No, it is because this is open programs. You cannot run this program. If it calls some external function, you don't know what will happen. And if the external function really modifies, somehow mutate your local state in somehow, so it's complicated. So that might be mutually recursive, mutually dependent. So you have to know that what the other modules can do to you, that what you can do to the other modules. So, but when you read, okay, yes, okay. Okay, so the point of compositional verification is that it allows you to modularize your verification effort. And it is essential for verifying large software systems. Okay, so today, in this talk, I will talk about, what I'm going to talk about is my recent work on developing proof methods for relational verification that supports interlanguage verification and vertical compositionality and horizontal compositionality. Okay, and then, but warning, but in this talk, I will not talk about Java and C, right? Rather, I will talk about higher language ML and lower language assembly. So Java and C I just used for example here. Okay, so Okay, so before I go into the details, I will tell you my overall overview of my work and then some lesson I learned. Okay, so I will start with some analogy. So, so in order to handle very well behaved children, like those who playing with lambda, you just maybe you can use a teddy bear, and then it works well for those guys. But if you handle ill-behaved children like a naughty boy playing assembly code by jumping on a piano, and then this teddy bear will not work. So in order to handle both children and then to understand the nature of children better, you may need a psychologist or a doctor, right? So similarly, so the most traditional proof methods for this relational verification care about only high-level, very well-behaved languages. Okay, so but they actually work very well for high-level languages, and they give us a lot of idea about the compositional verification. But however, if you try to use this method for relating high-level programs and the low-level programs, then they don't work very well because they oversimplify the problem by only looking at very well-behaved languages. So I had to come up with a new method, which we call parametric bisimulations, and that allows us to understand both high-level and low-level languages in a single unified framework. Okay. So the point here is that actually I've got a lot of insight from looking at assembly code. So the lesson is that don't be afraid of assembly. That might be a good boy for you. Okay, that's my overall work. Okay, so let me start. So as we have seen before, the relational verification is useful when you want to show the correctness of very efficient, real optimized implementation, just by showing that it is equivalent to some reference implementation, right? But there's also relational verification is also useful when you want to show that P1 satisfies some specification S. This might be very difficult to show directly because P1 is very complicated, or P1 is maybe written in a low-level language like assembly. So in this case, using relational verification, all you need to do is to show that P2 satisfies S, and that composed with the fact that P1 is equivalent to P2 implies that P1 satisfies S. So this also modularizes your verification effort. Okay. Okay, so, and relational verification has already been put to use in significant applications. In fact, the two most famous and most significant applications in full functional software verification, SEL4 and CompCert, made heavy use of relational verification. So first, secure embedded L4 is a fully verified, highly optimized microkernel based on L4 architecture developed at NICTA in Australia. For verification, they first formalized the handwritten informal specification of L4 as an abstract state machine. And then they wrote a reference implementation in Haskell, and then C implementation, efficient optimized implementation in C. Okay? And then they proved that abstract state machine and Haskell implementation are equivalent, and then also Haskell implementation and C implementations are equivalent. Okay, and then the whole development is 200,000 lines of code and proof. Okay. Oh, sorry. And then second, the CompCert is a fully verified optimizing C compiler developed in RIA in France. And then for verification, they proved each compilation path here represented by green lines correct by showing that each translation translates a program into an equivalent program using relational verification technique. Okay, so also CompCert consists of 50,000 lines of code and proof. So here the main proof method behind those two applications is something called simulation relation. Okay, and then simulation relation support the inherently support vertical compositionality. Okay, so in the specific case of compiler correctness, it means that here. Yes, you can compose this verification of each compilation path together to get the correctness of equivalence between this source program and the target program. Okay, so, and then this is really essential for CompCert verification because CompCert has 14 compilation paths, and the only feasible way to verify the compiler is to verify each compilation path individually. Right. However, but simulation relations do not support another important form of compositionality, which is horizontal compositionality. Okay, and then so in the it means in the compiler verification case, it means that the ability to compose together the verification of different modules, possibly compiled by different certified compilers, and some module possibly optimized by hand, and then compose these proofs together to get the equivalence between link to source program and link to target program. So that's the horizontal compositionality, but that's not supported by simulation relation. Okay.
Give an example of why not. I mean, is this like the different different calling conventions? Is that?
Not just that, because I like to think about this as one A.C file, B.C file, and the A.C may have external function from this B.C, and the B.C may have external function from F.C. They are mutually recursive, and then they may have access to the memory here, and this one also has access to memory here, the heaps there. So when you call this another function, since you don't know which compile you used here, so when you reason about when you verify this code, you don't know which compiler the other module will use. It can be arbitrary compiler, so you don't know what will happen here. But because of the difficulties, because of unknown module, so you have to prove the correctness against all possible modules and all possible compilers and all possible optimization by hand. You don't know what will happen if you call that function. Somehow you have to know that they will do something right, I will do something right, so somehow composition works in harmony. So the point is the openness. You don't have a full code.
I'm probably just asking the same question.
Okay.
So maybe I should let you go.
Okay.
On.
Okay. So because since the simulation relation do not support horizontal compositionality, the CompCert has a significant limitation, which is that its correctness is only guaranteed only when the compiler is used to compile whole programs without using any form of linking. Right? Only that the correctness is guaranteed. Okay, that's a quite significant limitation. Okay, so what we really want is to have both notion of compositionality, right? It means here that the equivalent by composing the verification of each compilation path here represented by green lines, we want to get the equivalence between this linked source program and then linked target program. Okay, and this is very challenging because you cannot compose the verification of TR1 and TR2 horizontally because the intermediate languages IL1 and IL3 are different. So you cannot link a program here, right? But somehow you should be able to compose the whole verification of this compiler 1 and then whole verification of compiler 2 horizontally because the source and target languages are the same, right? So you can't compose the individual ones, but you should be able to compose the whole one. So that's why intuitively difficult, and it's not obvious how to do that. Okay, so let me visualize the state of art in relational verification and my contribution. Okay, so simulation. So there are three axes: horizontal compositionality and interlanguage verification, vertical compositionality and interlanguage verification. And simulation relations are in this corner, which is support interlanguage verification and vertical compositionality, but not horizontal compositionality. And on the other hand, also, there has been a lot of work on reasoning about program equivalence in high-level languages like Java and ML. Okay, and one of the most advanced and prominent technique is curriculological relations, and we can simply call KLR. Okay, and this technique support horizontal compositionality, but not the other two. Okay, so you may want to make this simulation relation to support horizontal compositionality here, right? But that's not obvious. So I took another approach, which is to generalize curriculological relations to support interlanguage verification. Okay, and then here I gave the first horizontally compositional compiler correctness result, and this will be the first part of my talk. Okay, and then I tried to make this technique to support this vertical compositionality, but there was a fundamental problem with it, which I will explain later. So instead, what I did is I invented a completely new proof method, which we call parametric bisimulations, that supports both horizontal and vertical compositionality. And then I have a lot of confidence that by composing these two axes together, we can reach here. So currently, I'm working on generalizing parametric bisimulation to support the interlanguage verification using the ideas I used in this first work. Okay, and then there are also many other directions of future research, which I will discuss at the end of the talk. Okay, so let me talk about how to generalize curricular relation to support interlanguage verification. Okay, to motivate my approach to interlanguage verification, let me start talking about all the problem of program equivalence in high-level languages. Okay, so there we have a gold standard definition of program equivalence, which is called contextual equivalence. And then if we say the program P1 is contextually equivalent to program P2 if they produce the same observable behavior when linked with the same client C or same program context C. So here, the notion of behavior depends on what you want to observe. So for example, it may be simply divergence and termination, or it can be a sequence of inputs and outputs. Okay. And then, why is this gold standard definition? That's because it is the largest relation that's both vertically and horizontally compositional and also sound with respect to behavior equivalence. But the problem with the contextual equivalence is that it is hard to reason about directly because of this universal quantification over all possible client. So you have to consider all possible client in your proof, right? And also, more importantly, it does not scale to interlanguage verification because you cannot use the same context, syntactically same context C in different languages. For example, ML and assembly or Java and assembly, you cannot use same context. So it does not make sense. Okay. So what do we do? Well, actually, in practice, people don't actually prove contextual equivalence directly, and instead they use many various other proof methods, which is sound with respect to contextual equivalence. And as I mentioned before, the most advanced one is curricular relation, right? So it is, and then why is this a good proof method? Because it supports local reasoning about program equivalence, which means that when you show two programs equivalent, you can just reason about your local code, not reasoning explicitly about your all possible program context, right? Okay, and then another nice thing is that this logical relation do not fundamentally bake in the assumption that programs being related come from the same language. So what I did was I take this curricular relation as our definition of program equivalence between different languages. So then why is this good definition? First, curricular relation itself is horizontally compositional and sound with respect to behavior equivalence. Here I left out vertical compositionality. That's because curricular relations are not vertically compositional, which is a problem, but I will address the problem in the second part of the talk. Okay, and then also this relation is very large in the sense that it relates a lot of programs. Yeah.
But because they imply contextual equivalence,
yeah.
You get compositionality vertically.
Yeah. So.
So
oh no, this is subset, so it does not necessarily vertically compositional. This one is vertically compositional, but this is not. Not. But in the single language setting, you don't care about vertical compositionality of this technique because you have this contextual equivalent. You can use it yes, you can use this one instead, right? But now in interlanguage setting, you lose this one. There's no contextual equivalence. Okay. So you need something which is itself compositional, right? So that's why people didn't pay attention much attention to this KR's vertical compositionality. Okay, and then so it's a very large because it does not care whether the programs do different things internally, so long as their external behavior is the same. Okay, so but unlike other properties, this notion of very large is very informal, right? So what we really want ultimately is to show that this relation is large enough to verify many different compilers and also verify all possible handwritten assembly code, right? So, but this is a very open-ended goal. So to demonstrate this possibility, I verified a simple single-pass compiler from core-ML to assembly, and also verified a challenging example of self-modifying code for hand optimization example. Okay. So that's my work at last year Popple. And then here in this talk, I will not go into details of how I adapt this logical relation to relate programs between ML and assembly, because that's mostly about dealing with the low-level details of assembly and also very technical. So instead, I will focus on two things. One is to conveying the basic ideas behind the critical logical relations and why critical logical relation inherently support interlanguage verification. And the other is to demonstrate how to use critical logical relations through this hand optimization example, self-modifying code example. Okay, I will talk about two things. So first, let me talk about critical logical relations. Okay, first logical relation. So, question or okay. So, the logical relations can be best understood by looking at how functions are related. Okay, so, and then here, so these represent two functions which I want to relate, and then these are the two arguments to this function, and then here this one is function application, and this is also function application, and then which is a form of linking, because this argument can be functions. Like, for example, this can be callback function. In that case, this function application is kind of linking of two functions, right? Okay, so the basic idea behind the logical relation is simple. Equivalent programs take equivalent arguments to equivalent result. That's the main idea. So here, more specifically, you say that two functions are logically related if they produce the same observable behavior for any logically related argument, right? And then also, when they return, they have to, the return values should be related, logically related at type B. Okay, sorry. So, okay, let me see. Okay, and then here important point is that, okay, so point is that why then this inherently support interlanguage verification? That's because we always talk about related programs, not the same programs like contextual equivalence, right? So in order to emphasize this point, I use the angels on the left-hand side always, which to represent high-level programs, and then devils on the right-hand side to represent the low-level programs. Okay, so this idea is simple. Okay, right, and then what are critical logical relations? Critical logical relations are logical relations that generalize logical relations to handle languages with mutable state. Okay, so critical is for state. Okay, so for instance, in Java, these two functions may have access to some local state. For instance, if they are methods of some class with a private fields, then they have this access to its own private field. In that case, the issue is that this private field can change over time. So reasoning about that is hard. And the recent work by Dry et al. Has shown that the private state can be modeled using a state transition system. So like this. So here in this transition system, each state kind of determine an invariant on the local state. Okay, and then these transitions tells you that how the invariant can change over time. So this state transition system model two things: invariant and then changes of invariant over time. Okay, so the idea of critical logical relation is to index your logical relation by this kind of transition system. Okay, and then said that we say that two functions are equivalent at this transition system with respect to this transition system if they take equivalent arguments to equivalent result, but starting in arbitrary state, like this, you should be able to show that property in starting arbitrary state and ending in also arbitrary state, but that's accessible from whatever the starting state was. So for instance, if you start in this state, then you can end in either this state or this state, because these two are the only accessible state from this state. Okay. So let me give you a concrete example of this state transition system in the following example of self-modifying code example. Okay. Okay. So I will show you the example in stages. Okay. So this one is a high-level function, ML function, which is a function that takes a callback function f and invokes it and returns 1. It's a simple high-level function, high-order function. And then this is a straightforward implementation of this function in assembly. Okay, first, as a calling convention in assembly, we represent a function as a so-called closure, which is a heap cell containing a code pointer to its function body. So this is a function body which implements this one straightforwardly. And then this is the part which creates a closure. Okay. So if you execute this one, it first creates closure and then point to this function body bg plus 13. And then later, if closure is called, it will jump to here. And then first, it calls the callback function. And then if the callback function returns here, then it returns 1 to its caller. Okay? It's a simple implementation, right? And then to make it more interesting, I obfuscated the code by adding 666 to the code. Okay, so it will look like this junk. So it's hard to see what the instructions are. Okay, and then now let's walk through this example to see how it works. Okay, so first part also creates closure, and then this time bg plus 5. And then if the closure is called later, it will jump to bg plus 5, right? And then what it does first is decrypt this code. Okay, and then it overrides first instruction to jump to bg12, and then override its own closure with the bg plus 13. And then the remaining is the same as before. Okay, first, why I override here? That's for performance, right? If this closure is called later, it will directly jump to bg plus 13. That's okay because the code has been already decrypted, right? So it's faster. But then, why do I bother with this overwriting this instruction, even though this never jumped to bg plus 5? That's because actually this part can be executed several times, so it can generate several copies of closures. So some closure may still point to bg plus 5, right? So if this is called, it will go to here, and then thanks to this new instruction, it will jump to bg plus 12, and then updates its own code pointer. So intuitively, I hope you understand how it works, right? So any question about this code? Okay.
So
oh, yeah.
If there was any concurrency going on,
oh, no, not.
You'd be worried, right? Because
yes.
Decode it, then decode it again.
Sure. Yes. That's a very interesting problem which I will discuss in the future work. Okay. So here we only consider the sequential program. Okay. So now let's see how we formally verify this assembly code using quick logical relations. I mean, it's a very high-level proof. There's no technical thing. Okay. So the idea is that first, when this whole code is loaded into memory, you install some transition system, which basically says that, okay, the reason is because this whole code now is going to be used as local mutable state, right? So you install this some transition system, which tells you some invariant on this code. So it says that either this code is encrypted or decrypted, and then initially it is encrypted, and then it can transition to decrypted state, but not the other way around. Because once the code is decrypted, we know that it's not going to be encrypted again, right? So that's our intuition from the code. So this is what I install. So from the intuition, I install some invariant, and then I prove that according to invariant, this program is good. That's kind of usual technique, right? It's co-inductive technique, flavor technique, right? So I installed this transition system according to my intuition. Okay, and then after creating this closure, I install another transition system on this closure. It says that simply this contains either bg plus 5 or bg plus 13. Initially bg plus 5 and then transition to bg plus 13, but not the other way around, right? That's our intuition. Okay, now we have two transition systems with the two states, so we can merge them into single transition system with the 4 states. Okay, but if you look at these 4 states carefully, then you will see that this state is very weird. It says that code is encrypted, and then closure contains busy plus 13, which is here. So if you call this closure, it will crash, right? So, and then, but we know that from intuition, this never happened during computation, right? So we remove the state from the transition system because that's our intuition.
So there is a moment at which that holds after it has been decrypted.
Oh yeah, because yes, right. Because this is sequential language, so we just need to care about end-to-end behavior. If it's a concurrent case, we have to care about at each step. But it's a sequential, so you don't need to worry about the in the middle state. You have control, so there's no interference.
Yeah. So somewhere you need to say what the end.
Yes, the end-to-end. Yes, that's the only interesting part. Or the point where you pass the control to someone else. So like if you call external function which you don't know, then you have to make sure that I did something right for him. I didn't ruin his invariant or things.
So as the prover, you get these invariants from
Yes.
your intuition.
Yeah.
And do you also say, as part of your intuition, where the invariant should hold?
Yes.
That's part of what you
Yes. Yeah. Formally, the definition forces you to check that only the control pass point, right? So the beginning of your code or end of your code or in the middle, if you call some other external function, then at that point you have to check. I mean, that's not formally. I mean, somehow it's a kind of that's a reasoning principles. If you check only that point, you can prove they are equivalent. The logical relation supports that kind of reasoning principle. Okay, so it supports local reasoning in that sense. Okay, so where? Oh, yeah, and then also by the definition of logical relation, we need to check that for every state, for each state, if you call this function, this closure, it should behave the same as this high-level function, right? And then let's check just first case because the other cases are analogous. So in this case, okay, assume that we are in this state, then we know that the code is encrypted, and then this closure contains bg plus 5. And if we call this closure, it will jump to bg plus 5 state, and then it will first decrypt the code, and then actually I just said you don't need to move the transition because currently still I have control, so you don't need to check this state. You just need to check end-to-end. But just for animation, it moves here. So basically, the code is decrypted, and it still contains bg plus 5. So we move to this state. And then we update this code pointer with bg plus 13. Then we can move to bg plus 13 state. So we can transition from here to here because it's allowed, right? And then that's what we did in this code. So we can change at this point, we can change the state to here. Okay, and then, okay, so the remaining code is the same as before, so we can easily show that it is equivalent to E1. But here, important point is that now we are in this state, which is the state with no successor. So according to this state transition system, we know that we always, in the future, we always stay in this state because there's no outgoing edge, right? So the point here is that when the callback function returns at this point, right, then what we know is the callback function didn't change our local code because there's no way, we cannot move out of this state. Right? In general, I called some callback function, it can do whatever it likes, but since it respects this, since we assume that it respects my transition system, it cannot change the state. So I know that the code is still decrypted. So I can execute the rest of the code. Okay, that's the important point. Okay, so this shows kind of how the proofs works at very high level. Okay, let me see. Okay, so to summarize, so I defined the logical relation between ML and assembly, and then verified some compositional compiler correctness result, and then hand optimization code equivalence. And then the important point here is that I can link any program compiled by this compiler, and then this naughty hand optimization code together. And then it's automatically guaranteed that this linked program behaves the same as this linked program. This is a self-modifying code, right? So this is what we can support, and this is what CompCert does not support, right? Okay, so there is another key challenge, which is dealing with the garbage collector, but I will skip it because I don't have enough time. Okay, so now let's talk about how to support vertical compositionality. Do I have time? Okay. right? So in order to motivate the key ideas behind the parametric bisimulation, let's first start to prove the vertical compositionality of logical relation between different languages and see what's the problem. Okay, that helps to understand the basic idea of parametric bisimulation. Okay, so in order to show that this logical relation is vertically composable, we first assume that F1 is equivalent to F2 and F2 is equivalent to F3, and then now we need to show that F1 is equivalent to F3. That's what you want to show, right? And then by definition, we have to show that for any equivalent argument V1, V3, F1 applied to V1 and F3 applied to V3 behave the same. That's what we need to show. And then also, in order to use this definition, what you have to do is we have to synthesize some program, V2, in the intermediate language, such that it is equivalent to V1 and V3, right, in order to use this definition. Okay? Is that clear? Okay, and then, but in general, it's not obvious that whether such V2 even exists here, right? This is some intermediate language which is different from these languages. So actually, the reason is because V1, V3 may come from completely different modules. And then they may be related for completely different reasons. For example, they may use a different set of intermediate languages, right? In the proof of V1, V3 equivalence, they use some other intermediate languages. They may be different from this one. Okay, that's the reason why logical relation does not support vertical compositionality. Okay, here's my observation is that there is not necessarily a single notion of equivalence, which makes sense for all the modules, like my module and external module. So we don't need to use the same equivalence. That's my observation. Okay, so that led me to develop a parametric bisimulation. And then the idea behind it is that we allow each module invent its own notion of equivalence, which this module-specific notion of equivalence we call local equivalence, and which is denoted by this blue equivalence. Okay, and then we say that also the global notion of equivalence, global equivalence, is kind of a union of all the local equivalences for all modules. Okay, that's intuition. Okay, and then we use that global equivalence to relate this argument because we don't know where the argument came from, because it's unknown code, right? We are linking against unknown part. So we use a global equivalence here. Okay.
Wait, why is it that way? I thought these were just linking. That's a sort of peer
operation.
But you seem to be saying that the Fs are somehow different than the Vs, that the Vs must be globally equivalent.
Yes.
But the Fs can be locally equivalent.
Yeah, because you know what this code is. You are proving this program equivalent. So you know exactly what the program is. You wrote down this program. So you know, but this one is given from environment. You don't know what it is, what they are. So we just, since we don't know, we first kind of intuitively use some global equivalence. I don't know what it is. So the tricky part is that we don't know what this global equivalence is. We have no information, right? Okay, so the idea is that since we don't know what it is, so it can be anything, right? So we parameterize our whole model over arbitrary global equivalence. So the only restriction on this global equivalence is that it at least should contain my local equivalence, which relate to F and F3. Because kind of intuitively, this is union of all the equivalence. So it should contain mine, but we don't assume anything else. Okay? So that's kind of intuition, and then let's see the definition. Okay, so I will, parameterize over global. Okay, that's the idea. Okay, that's why I call parametric bisimulations. Okay, and then I will show you the definition in stages. First, what you see is the logical relation. Okay, so they defined a single notion of equivalence, which relate both functions and argument, right? So now, parameterize it. So my functions are, now parameterized. So I quantify over arbitrary global equivalence, and then I use them to relate my argument. Okay, so more specifically, it says that my functions are equivalent if they produce same observable behaviors for arbitrary global equivalence and arbitrary values related by it. Okay, and then you can see that this doesn't make sense because here the functions cannot behave globally the same because argument comes from arbitrary relation, so they may behave differently. So if my function calls this callback function, then we don't know what will happen, so we cannot show the global equivalence. So what we require is instead is to say that only local behavior of these functions be the same. Okay. So let me show you what I mean by that. So I will explain the notion of local equivalence using an example. Okay. Here, so this function assume that this function is this high-level function f, which take a callback function, and also this function is some assembly function f. Okay, and then this callback function argument, so this one is passed in as g, and then this one will be passed in somewhere in the store, in the stack, sorry. And then we assume that these arguments are related by global equivalence. That's a kind of assumption of my parametric bisimulation, right? So now I show that these two functions behave locally the same. For this, I first execute them, okay, and then show that they produce the same observable behavior. But in the middle, if this calls external functions here and here, then we don't know what will happen. Since this relation is arbitrary, it can be bound. So if you try to execute this one, it may explode or crash your system. So we should stop reasoning about that. But instead, what do we need to do? Then, okay, sorry, boom, sorry. Okay, then what you need to do is, what you need to show is that the function you are really calling are related by the global equivalence. You don't care about the behavior. Just I called some functions which global relation says they are equivalent. I don't look at the code. I don't care about the behavior, right? So then how can you show that the functions that I call are equivalent by this equivalence? That's easy in this case because as long as this EAX register contains the original callback functions passed in as argument, then I know that these are equivalent because that's assumption. That was the given assumption. We assume that the arguments are globally equivalent, related by global equivalence. So as long as I call them, I know that they are globally equivalent. So kind of I checked the right thing, right? I didn't do anything wrong, right? And then what I do is assume that these external functions return properly here, right? And then continue reasoning about local behavior equivalence. So the point here is that I only reasoned about my local code. I didn't reason about any other external code. So
what you have to assume, you assumed about G that it was read equivalent,
yes,
globally equivalent.
yeah.
And that implies that it's locally equivalent. Because that's
That's assumption, yeah.
Okay, so here,
that's implied by local equivalence. Local equivalence is a subset of that. Oh, sorry.
Globally equivalent implies locally equivalent?
No. Local equivalence implies. So global equivalence is bigger than my local equivalence. So it can be arbitrary thing. It can even relate to BOM, right? So we don't assume. So basically, since we don't really care about, intuitively, since we don't really care about other external modules, in the proof method, we don't assume anything. Allows kind of, so this basically localizes your proof more, and more localize your proof. Your proof is really local. So the point, then the thing is, the point is that since each module is responsible for only its own behavior and they don't care about behavior of others, you can easily link them together. So because no module assumes anything about other modules, so they can be composed easily. So that's why parametric bisimulation support horizontal compositionality intuitively. Okay.
Sorry, the measure of behavior.
Yeah.
Must include something like a trace of the number of times G is called, or the sequence of calls to G.
Yeah, that's fine. Yeah.
Right.
Yeah, that's fine. Yeah, but kind of intentional. Some like this is we don't want to think like the number of steps. So some function is faster than the other. We don't want to care about. I mean, the computation cannot check how many steps it took. Like that intentional behavior, I don't want to observe, because then we cannot optimize, right? If you observe kind of speed, then you cannot optimize anything. But number of functions, the number of function calls, that you can check. Yeah, because you can print out the number of function calls. Yeah, so that's a part of observation. Okay, so it supports horizontal compositionality. Okay, so now the key part. So I will show you the key high-level idea behind the proof of vertical compositionality. So why this proof method? 10 minutes. Okay, why this proof method is a vertically compositional? Okay, so also Also, to show this vertical compositionality, let's assume that F1 is equivalent to F2, and F2 is equivalent to F3. Okay, now I need to show that F1 is equivalent to F3. Okay, so by definition, I need to show that for any global equivalence, and then for any related argument by that global equivalence, I need to show that F1 applied to V1 and F3 applied to V3 locally equivalent, locally behave the same. That's what you need to show, right? Okay, also in the same way, in order to use this equivalence and this equivalence, what I do first is I decompose the global equivalence into two, right? In such a way that it relates V1 and BOM and V3. And also, I somehow uniquely encode this V and V3 in this BOM. Okay, and then we know that this equivalence is a parametric over arbitrary equivalence, arbitrary global equivalence. So we know that F1 applied to V1 and F2 applied to BOM locally behave the same, even though this is BOM, because it does not execute this part, only local part, so we know that. And similarly, also, we know that these two are locally equivalent. Okay, now what we need to show is this local equivalence is transitive, but that's not obvious. Actually, but that's transitive because of this BOM. So, so the high-level idea is this BOM synchronize these two local equivalents. So to see this, let's suppose that F2 calls some external function, right? And then the external function should be BOM because we decompose in that way, right? So if this middle program calls external function, it cannot proceed anymore because it's a kind of crashed state. I mean, if you execute further, it will crash. So you should stop here. It's forced to stop here. Stop reasoning about that, which means F1, this part also logically should stop reasoning about its code because we are relating programs, and if this you cannot further execute this, also you should stop reasoning about that. And then the only way to stop reasoning about it is calling external function, right? So we know that F1 will call some external function, and then also somehow this uniquely encodes V1 and V3. So we know that that external function F1 calls is V1. And then similarly, also here, F3 is forced to call some external function, which is V3. Okay, now what we know is both F1 and F3 calls external function, right? Then, and by definition of parametric bisimulations, what we need to check is, so in order to stop reasoning about here, you need to check is V1 and V3 are related by original global equivalence, right? We have to check that. You can stop here, but you have to check that what the functions you are calling are related by the original one. But since this V1, V3 one is given originally, and we assume that they are related by global equivalence, we know that they are related, right? So we know that F1, V1, and F3, V3 locally behave the same. So the key part is this this smart encoding here with the BOM makes this synchronized. Right. Okay. So the one point is that global equivalence is arbitrary. That's really important. It should be able to allow arbitrary code, even BOM or some junk code. If it allows only good programs like logical relations, then you cannot prove this. So that's the key point. Okay, so that's local equivalent. Fine. Okay. So using this idea, we proved this both vertically and horizontally compositionality. And then the proof was quite tricky. I mean, intuitively tricky, but using this BOM idea and then parameterization over arbitrary relation, we can prove this tricky property. Okay. Okay, so here there is another challenge, which is that in this transitivity, this vertical compositionality proof, actually handling state is very challenging. That's a kind of orthogonal problem. So we handled that problem and we proved the vertical compositionality. But I don't have time to go into the details. But main thing is we have to think about shared state and local state. And then in the proof, composition of the proof, somehow you have to compose this shared and local state. But the shared and local state in this proof and this proof may not match exactly. So in this proof, this memory was shared memory, shared state, but in this side, it may be local state. Somehow you have to come up with some idea to handling that. Okay. And then, okay, so everything is fully mechanized in core. Okay, so we have seen this parametric bisimulation. And then also, you can sense that we can generalize it to interlanguage thing easily because the intuition came out of relating different languages. I consider the all languages are different, right? And also, since the global equivalence is arbitrary equivalence, even we don't care about whether it's the same language or not. So, yeah, I'm working on this, and I have a lot of confidence that this is not difficult. Okay, and then another important point is that actually this parametric bisimulation seamlessly generalizes simulation relation. So this is exactly the generalized version of simulation relation for open programs. Simulation relation is basically for closed programs. It relates completely closed program. You can run it. So during execution, they are synchronized, right? But if it has open component, some external function, then you don't know what happens, so you cannot use simulation relation. But this parametric simulation relation is basically generalization of it. You just check simulation locally, and if you have a unknown function, you come up with you just parametrically prove over arbitrary relation. So actually, good thing is, like CompCert proof use a simulation relation, and I can kind of reuse most of proof because this relation generalized this one. So I can use existing CompCert proof, and then I can actually generalize existing CompCert proof, turning into the kind of supporting horizontal compositionality using this new technology, new proof method, which I'm currently working on. Okay. So parametric bisimulation actually generalize simulation relation, and then also support all the reasoning principles of logical relation, correct logical relation. So it married together the benefits of both techniques. Okay, so let's talk about future directions of research. Directions of future research. Okay, so first I'm currently working on this interlanguage parametric bisimulation, right? And then I want to show some compositional compiler correctness result for multipass compiler for CoML. Previously, I only verified the single-pass compiler because it does not support the vertical compositionality. But now we can do that, so I want to demonstrate it for some compiler. And then I'm really interested in concurrency. Okay, that's because there are many interesting relational verification problems in concurrency. So for example, the one efficient implementation using fine-grained locking or non-blocking algorithm is equivalent to a sequential implementation using atomic block, right? So that's relational verification, and we can use a relational verification technique. And also, since bisimulation works very well for concurrency, I have strong confidence that this also works well for concurrency. So I'm working on this generalization. Okay. And then second, as I said before, I'm working on C4 project with Victor Vafeyades, and we are just adapting the existence, the proof compiler correctness proof of this CompCert TSO, which is variant of CompCert for concurrency targeting x86 with the TSO memory. So we are changing the underlying method. We use parametric bisimulation instead of simulation, and then make it to support horizontal compositionality. And we expect the most proof we can reuse. Okay, and then also I'm interested in supporting richer types, because currently this only care about consider unrestricted effects like references in ML. But if you have richer types which support restricted effects like monadic types or effect system, then you can prove more programs equivalent, more interesting programs equivalent. So I'm working on this direction, supporting more types. And then interlanguage linking, which is that kind of linking between ML and C through foreign function interface, or Java and C or other languages. And then I strongly believe that this should work because, as you see, we didn't assume anything about the other modules. It's completely parametric, so it can be different language. So my external module might be C, my module might be ML. That's okay. So through a foreign function called interface, if we formalize this interface formally, then they should support this linking. So that's another thing I'm thinking of. And then, okay. And then other thing is kind of maybe also formally formalizing this interaction with the system calls or operating system. That's also interesting thing. Okay, thank you.
Okay, thanks a lot, Gil. So we have time for some questions.
Yes.
Mr. Question.
So if you had to do some generalization to go from a single language to interlanguage,
Yes.
that was the main big point of your talk.
Yes.
So sometimes when you do generalizations,
Yeah.
you pay a big price. There's a lot more complication, but you get a benefit, but you pay every. And sometimes you think, oh, we should have done this generalization all the time because it was so easy.
Yes.
So where is this?
I think the second case, the latter case. Yeah, I mean, I personally think that this parametric bisimulation is at least simpler than the logical relation, because actually one thing I glossed over is logical relation uses kind of step indexing, which is very dirty part. Because one thing very interesting thing is, which I didn't mention here, is that if you look at the definition here, here, you see that this definition is well defined. Because it's a cyclic recursive definition, so it's not clear whether it's well defined. But in this definition, it's just well defined because this is monotonic. So meaning that if my local equivalence gets bigger, then you have a less number of global equivalence, right? So more programs satisfy this equivalence.
So can you kill off step index?
Yes, of course. And then if you look at the step index, okay, so I will show you the problem with the logical relation, which I didn't. Okay, shit. Sorry. Let's go back faster. It's too slow. Oh, no, I went back too much.
There are other methods.
Okay, so the problem with this logical relation is that, come on, here. Come on, right? Here, this is not well defined. It's not clear. See, here, this recurs in negative occurrence. This is negative occurrence. If this gets bigger, then you have to consider more related programs. So it's negative, so it's not well defined in general. But originally, they did induction over these types. But if you have richer types, like recursive types, you cannot do induction. So they use the step indexing. But in my definition, it's just inherently monotone. Okay.
Oh, so you should have done this all the time.
Yes, that's what I'm saying. So my lesson is look at assembly. Then you get the intuition. Okay. Yeah, so you see, this is well defined, right? So you don't need any step indexing. It's just monotone. If you get more programs, if your equivalence gets bigger, you have less number of equivalence, global equivalence, right? Which means more programs satisfy this one. So it's just defined by co-induction, or more fancy word, Knaster-Tarski fixed point theorem, rather than step indexing. So yeah, I believe this is better than, yes.
So does that mean you would apply this even just to high-level languages with lots of recursive features?
Yes, I can apply, yes. So I mean, the popular paper is only about ML language. We didn't do interlanguage. I mean, just to show the power of this method, we just, because it's easier to present the idea. Okay. So, yes.
So does it show all the same equivalences that you
there is one slightly subtle equivalence, which is that the eta equivalence. So in ML, in logical relation, they can show that function f1 and f2 are equivalent. I mean, eta expansion of functions are equivalent. Lambda x dot f, x, and then f is equivalent. But in my definition, we cannot relate them. But there is some good reason. Because lambda x dot fx did something to f. If your context can compare the function pointers, then function pointer of lambda x dot fx and f is different. So if you have completely unrestricted effect, you should not even assume that. Whether your context can compare function pointers or not, you should not assume that. So in general, there's no reason to believe that they should be equivalent from from point of view of my context. So logical relation, they assume that everything well behaved, right? Everything well behaved. I only care about these nice children, so they can get the equivalence. But here we cannot get. So my point is, if you have more precise, richer types, which somehow say that okay, my context cannot observe this one, then I want to prove that equivalence. So it depends on how you design your types. Your types should tell you that what can happen. That's the basic interface between my context and my program. So currently, I'm considering unrestricted effect, so I don't assume anything. So it should not hold.
But then you couldn't, sure, that would be very restricted.
Sorry?
Now you could never replace a function that, I don't know, added up the numbers between 1 and 10 with the function that returned 55.
Uh,
Because,
a
of
big-
course, the customer
Yeah.
could look at the code and say, aha, I can see you.
Yeah, I don't know. But the thing is, we only link together locally equivalent programs. And that these locally equivalent programs does not relate such functions. Like assembly, you can do anything. There is assembly program which look at the instructions and then syntactic equivalence, but that's not related by my equivalence. So as long as you compose together equivalent program by my relation, it always relate good programs. That's why I know that the other component don't ruin my local invariant. If I link with after the assembly code, of course there's a possibility that it just scan all the memory and then change all the cell with 0, 1, 0, whatever. So it can break my invariant. But since I'm linking with, so this compositionality means only link with the equivalent, the programs which are related by my relation. So kind of my relation gives you notion of, if we can define this also unary version, which means that just it gives you semantic types. So basically, programs which are related to itself by this relation can be seen as program having this type. So by this relation, we can carve out ill-behaved programs. Okay, make sense?
Okay.
Okay.
We'll have to take further questions later in the
Okay.
talks. But let's thank Gil again.
Okay, thank you.